So we're going to be starting Unit 4 here, covering in the Grade 10 academic curriculum, and I'm actually going to cover several topics all at once, including common factors, which is a review of Grade 9 concepts, and I'm going to go through a couple of other ones. So we'll just start off with the quick review of common factoring from Grade 9 and a few other little details. So common factoring, first of all, factors involve multiplication. So when you talk about factors of 12, you're looking at two numbers that when multiplied together give you 12. In actual reality, you can get more than one number multiplying, more than two numbers multiplying together to give you 12, but we're going to just be taking a look at two for other principles we're going to be looking at later on. So this concept also applies to algebraic expressions, where if you're looking for factors of 12xy, the 3 and the 4 can be used, and you can also separate the x and the y. So the two separate factors are the 3x and the 4y to give you multiplied together 12xy. Common factors, if you think of what people have in common, features. So algebraically, common factors means factors that are in common to two different expressions. So, for example, the greatest common factor, G, C, and F, that's the abbreviation here, of 12 and 16. So they have to have a factor in each of them, but we're looking for the greatest one. So in this particular case, even though 12 can be written as 2 times 6, and 16 can be written as 2 times 8, 2 is a common factor. However, it is not the greatest common factor. All right. So if you think about all the factors of 12 and 16, sometimes that's one way of looking at finding the greatest common factor. There are other techniques you can take a look at online. You'll be able to find something. So if you write out all the different numbers that could be factors of 12 and the different numbers of factors of 16, and then find the largest in common between the two sets, in this case it's 4. So what we say is that the greatest common factor between 12 and 16 is 4. And as you can see, 12 can be written as 4 times 3, and 16 can be written as 4 times 4, and they have the 4 in common. All right, so that takes care of a little explanation in terms of the greatest common factor. Again, that's something from the grade 9 program. And if you add variables, now this is a different way of looking at it. So what I've done here is I've listed all the factors for this algebraic expression with the common values already in place. So we have the common factor of 4, the greatest common factor of 4, for the values 12 and 16. And then 4 times 3 will give us 12. 4 times 4 will give us the 16. Now, in terms of the variable portions, the x to the power of 4, that means I can write out x as a multiplication 4 times. X to the power of 7, x is written out as a multiplication 7 times. And again, between these two, how many x's do they have in common as factors? Well, there's 4 here multiplied together, and there's also a grouping of 4 here. So the greatest common factor for 16x to the power of 7 and 12x to the power of 4 is the coefficient, the number 4, which is common, and 4 of these x's. So that tells us that the greatest common factor for these two expressions, 12x to the power of 4 and 16x to the power of 7, is 4, because it's the greatest common factor between 12 and 16. And x to the power of 4, it's the greatest common factor between x to the power of 7 and x to the power of 4. Now, a quick way of maybe cheating, I suppose, or getting to the commonality in terms of the algebraic factors is looking at the lower of the exponents. That will typically lead you to the correct result. So, a few more examples, looking at these ones here. Again, just looking at the variables. So what do these have in common in terms of factors? Well, again, as I mentioned just a moment ago, the lowest exponent will always produce the greatest common factor. Here, between these two expressions, this one here has the lowest. That produces the greatest common factor. Between these two, the lower number again, produces the greatest common factor. This gets to be a little bit trickier, so you're looking for the lowest exponent for the x term, which is a 3. Hence, the x cubed is part of the greatest common factor. And then the lowest between the y terms, which is a 3, so y cubed. So this entire expression is the greatest common factor for those two different expressions. Some more complex factoring involves taking a look at this situation. We have a binomial, 2 terms. And what do these 2 terms have in common in terms of factors? Well, the 2x can be written as 2 times x. The 6 can be written as 2 times 3. And as you can see, they have a common 2, which is here. Now, the remaining factor comes from the remaining x and the remaining 3. Now, why is there a plus? Well, because that's what the operation is here. And as you can see, using a distributive property, you would wind up with the same result. 2 times x is 2x, 2 times 3 is 6. So factoring is the opposite of expanding. So here we have expanding, distributive property. Factoring is a process whereby we take the expanded form and write it in factored form. Okay, so we're going to be taking a look at a couple of other items just to make sure this is clear. So we've already seen factored form, where you can expand and distribute to get standard form. And there's that same example we just looked at, and a follow-up one as well down here. So what does the 6 and 3 have in common in terms of factors? Well, it happens to be the 3 that they both have in common here and here. So that's your greatest common factor. And the remaining values, the 2 plus the 1, but it's a 2x. So you have to keep that in mind, because what you're trying to do is develop a greatest common factor that when you multiply by the remaining terms through a distributive property, the result is what you started with to begin with. Okay? Okay, so we're going to be moving on to section 4.2 of the book that explained factorization of trinomials. 4.1 was really just looking at some grade 9 content and factoring of binomials and some other terms. So this is just a quick exploration as to one of the patterns that does exist in terms of one of the techniques we're going to end up using. But we have to establish some terminology here. So the goal is to discover the relationship between the coefficients, which are values placed in front of variables, typically to the left, and constants, which are just values that are part of the expression, but just numbers all by themselves, in a trinomial, which means they have 3 different terms. So something with an x squared, something with an x, and then your constant on the end. All right. Okay, so in this particular case, we have a situation where we're going to take a look at the distributive property to help us determine what this pattern is. So through the distributive property, and I've written this out very slowly for a reason, you'll see why in a minute. So when you multiply the 2 x's together, you could get x squared, but I'm going to write this out just so you can see exactly where these patterns are developing that we're going to be using in a moment. So everything here is a straightforward distributive property. X times x, x times 4, 2 times x, and 2 times 4. And to simplify a little bit, so the 2 x's multiplied together, you give the x squared, the x and 4, the 4x, 2x, give the 2x, and the 2 times 4 give you the 8. Now, it's not a matter of just simplifying, it's a matter of using this technique to see if you can find a pattern. So, what we're looking at is a way of starting with this yellow highlighted part, and is there a way to go backwards and determine the factored form? So one of the techniques involves what we're going to be talking about is looking at the factors of 8. Now, why is that important? Well, let's take a look up above here. These numbers, the 2 and the 4, they were both used in the expansion, weren't they? So they play a very important role in determining what could be the factored form. So these two numbers multiply together to produce the 8. So we need to consider the factors of 8. Typically, it would be the factors of this constant, whatever that constant is. Now, if you notice, the factors, the 2 and the 4, they multiply together to give us 8. How do we get the 6? Well, the 6 was produced by adding like terms, but more importantly, adding 4 and 2, which are exactly the same numbers that were the factors of the 8 that were used. And that's part of the trick. So, factors of 8 that add to 6. So you're not just looking for any factors of 8, because you could have used 8 and 1. 8 times 1 does give you 8, but 8 times 1 does not produce a 6. Okay? So you're looking for very specific factors that are going to help fill in this pattern. Let's take a look at another one. So here, if we distribute this exactly the same way as we did before, now this one you got to be careful, it's got a bit of a negative sign in here. So -5 times the x, -5 times the 3, so I've written it out that way. So this will produce, again, there's the highlighted part. So what we're trying to do is find a technique to come back here. Now we haven't discussed the bracketed portion yet, we will in a moment. But the key thing is trying to find factors of -15. But not only just any factors, but we want these factors, as you can see, -5 and 3 are both used in the expansion. So if we're starting with this expression, what we're trying to do is look for factors of 15 that when we add them together, we wind up getting -2. And the answers are -5 and +3. So -5 times +3 multiplies the -15. Those are the factors we want. And those same factors add to a -2. Now, if you look at the bracketed part, -5 is inside the bracket and a +3 is inside the bracket. Let's see if that worked for the previous one. So the previous one, we had factors of 8 were 2 and 4. That added to 6, multiplied to 8. Let's look inside the brackets. +2 and a +4. So we have a quick little pattern for determining how to find the factored form. And this works when the coefficient of x squared is 1. So this trick that we're looking at only will work when we're trying to factor trinomials that have this kind of a look to it. Okay. So if we're looking at factoring x squared plus 8x plus 12, so we're looking for two numbers that multiply to 12, and the same two numbers give you a +8. That's the quick way of coming up with a result. So you can write down the list if you want. 1 times 12 will give you 12, but they do not add to 8. 2 times 6 will give you 12, and that does add to 8. But if you were to try even negatives, -3 and -4 do multiply to +12, but they do not produce a +8. So this is the correct values that we're looking for, +2 and +6. So how do we use that to factor? Well, because it's in a particular format, the first portion of the brackets are x and x. And that makes sense because x times x gives us x squared. Because we have the numbers 2 and 6, that's going to be the second part of the binomials. Whoopsie, that should have been a 6. In the bracketed part. So you have the x at the beginning, because x times x produces x squared. And then because of this technique up at the top, the 2 and the 6 are going to be our values that we're looking for inside the brackets. So this is referred to as factoring a trinomial when the a value or the lead coefficient is 1. So this trick will work all the time. There are other techniques that we're going to take a look at, and you can look online for other techniques, but this is one of the most simplistic ways of factoring this type. Okay, so just to carry on with what we were already looking at, so you'll notice we're again factoring quadratics in this format. So notice the a value, it doesn't even exist in the form because we're going to use a 1, right? So it can be factored into this format. You might be wondering, why is there a letter A here? Well, sometimes there could be a common factor, so we're going to have to take a look at that in some of the more complex examples. All right, so again, if there exists two numbers who the product is the C value and the sum is the B value, then we can factor it. Now, the interesting part with factoring is sometimes trinomials in this format are not factorable, and that is a possible answer. So you could have a question that is not factorable, and that would be your answer, that it's not factorable. But the golden rule you have to understand for any factoring question is always look for your greatest common factor. Always, 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 always. So we're going to go through a few factoring examples and making sure that we do or don't have a common factor, and if we do, is it a trinomial? And if it is, then we're going to have to use a technique to try and factor that further. So we have a trinomial. That one there is one of those hiding ones, and it's there just for a reference. Okay, so we do have a trinomial. Is there a greatest common factor? The answer is no, because there's nothing the three of these terms have in common. These all have a value of 1, 1, and 6. Now the only common factor is a 1, which is not helpful to us. So there's no common factor, greatest common factor, but it is a trinomial. So we're looking for factors of -6. That's what we want right now. We want factors of -6. Just going to use that, switch over to my magic pen, sorry. So we have a trinomial with no greatest common factor. So we have to use the trinomial technique we just looked at a moment ago from 4.2. Take a look at the constant. Think of two numbers that multiply to -6, but you want these two numbers to add to +1. So these are possibilities that are factors of -6. But the grouping or the pairing that works to give us a +1 when you add them. So here's a way you can write down your rough work, the product. So these two numbers will multiply to -6, and you want the same two numbers to add to 1. And again, this is coming from the constant. This is coming from the B value, just as it's mentioned up here. So the product is C, sum is B. The product is the -6, and the sum has to be a 1. So the two numbers that produce a product of -6, and the same two numbers that produce a sum of 1 is -2 and +3. So you notice they're written in here, and automatically the first portion of the bracketed parts are X and X. All right, next question. So again, is there a greatest common factor? Well, no, not all three of them have the letter X, so definitely no variables common. And again, there's no constant value that is common in terms of a common factor. So there is no common factor, but we do have a trinomial. Yes, we do. There's three different terms. So again, we're back to this technique. We're looking for the product and the sum. So two numbers, we want two numbers that multiply to 28. So we want 28 equals the product of two numbers. So you can go ahead and just start guessing wildly, which will work. It'll be a trial and error, but the numbers you're looking for that multiply to 28 also have to add to 11. Don't worry about the X, just have to add to 11. So this really kind of relies on using some mental math skills, which you can always practice your times tables to get through. 4 times 7 will produce a product of 28. Now the question is, does 4 and 7 add to +11? And the answer is yes, it does. So these are the values we're going to use in the bracketed part. And then once again, having the X's inside the bracketed part as an automatic feature of this technique. All right. Now, these remaining ones down below, again, it's the same question over and over again. Is there a greatest common factor? Very repetitive. You have to be robotic with this. The answer is no. There is no number that is common to all three other than 1, which is not helpful. So we're looking for two numbers that multiply to 10, add to a -7. Now, when they add to a negative and multiply to a positive, well, you have to keep in mind that two negative numbers will multiply to a positive, and two positive numbers multiply to a negative. But the question is, do you want two negatives or two positives here? Well, if they have to add to a negative, it would make more sense to have the values that you're looking for be negative. So the two numbers that multiply to 10, well, probably most of the ones that come to mind are 5 and 2, but you want them to be negative. And why would you want them to be negative? Well, simply because you're looking for the result of the sum of these two numbers to produce a negative 7. So I've abbreviated the little work up here up at the top where it says product and sum, and just use P and S. And again, then once you find those numbers, the x's are automatic inside the brackets, and then you just put the numbers in there that work for your pattern. Okay. Similarly with this next example, it doesn't matter if it's an x or not, but product, sum. And again, there's no greatest common factor to worry about. Two numbers are multiplied to negative 33, or negative 3 and 11. And again, that might be a little trial and error before you figure that out. And you might have the negative sign in the wrong spot too. So you might initially start off with a negative here and a positive there, but that's okay. This is why it's important to write the work down. And as soon as you discover which pairings work, those are the numbers you use. So these two numbers have to add to a positive 8. Once you find those numbers, you're writing it in the pattern as we have here. And instead of using x, because the expression started off with a w, we have a w inside the brackets instead of an x. All right, now in this next one, although it doesn't look like it, notice the number in front here is not positive 1. It is a negative. So yes, we do have a greatest common factor. It actually happens to be a negative 1. So positive 1 is not useful as a common factor, but negative 1 is very useful. So let's take a look at what happens here. So with this one here, if we rewrite it with a negative 1 in common with the factoring process, so negative 1 times x squared will give us negative x squared. A negative 1 times a positive 24 will give you negative 24x. And to write this one as a negative 1 times 144. So negative 1 appears in each one of these three terms. So it becomes a greatest common factor, leaving the remaining portions, x squared, 24x, and 144 as an unfactored portion. Now, even though this is unfactored at the moment, as you can see below, it has been factored completely. Why? Well, because this is a trinomial. So again, we're looking for the product now of, the product of two numbers that multiply to 144, but the sum has to be 24. More than likely, the most common numbers that come to mind for two numbers multiplied to 144 are 12 and 12. And luckily for us, they both add to 24. So the factored portion for the trinomial becomes x plus 12 and x plus 12. Now, as an added little feature, because these two factors in brackets are identical, the short form for writing this would be negative 1, so there's your greatest common factor here, multiplied by x plus 12 to the power of 2. So that's a short form for writing these two, just like you would write x times x equals x squared. So when you multiply two things that are the same, you can shortcut the writing by writing with an exponent. So two things multiplied together that are identical produce a shorter writing way, x plus 12 to the power of 2. All right, just to get a little bit more complicated. So here we've got lots going on in here. Now, every single one of these terms has the letter P in it. So automatically, there's definitely going to have something in common. Now we're looking for the greatest common factor, but there's also a factor of 2 here. There's a factor inside of 24 of 2, because 2 times 12 is 24. And definitely 2 will go into 70, so 2 times 35. So there's actually a 2 as a common factor as well. So the greatest common factor for this expression is 2p. So 2p is your greatest common factor. And the remaining portion that wasn't part of the commonality is m squared. a 2 and the p was removed as the common part here, leaving 2 times 12 m, and then the 2 and the p were removed here, leaving the 35. So when I say removing, it can be thought of as used as a division process, because remember, distributing involves multiplication. But you can think of the factoring part as a division. So if I were to divide 2pm squared by 2p, you get m squared. If I divide 24 by 2, I get 12. If I divide pm by p, I get an m. 70 divided by 2 is 35. P divided by p, well, they'll cancel each other out and left with nothing. So that is another way of thinking of this common factoring process from the previous lesson. And that's the unfortunate part about dealing with factoring, is that oftentimes there's more than one technique. So you're going to have to find the technique that works for you, whether it's what I'm discussing here or something else online. You also have a trinomial remaining. So what you have to do now is check this product and sum technique. So you're looking for a product, two numbers that multiply to 35, and the numbers that then add to 12, assuming they're the same. Are they the same? So two numbers that multiply to 35 are 5 and 7. Do these numbers add to 12? They sure do. So that means that the 5 and the 7 are going to be part of the final factoring step. And again, because of the expression, the trinomial has the letter m in it. M is kind of a given at the beginning of the bracketed portion. So two bracketed portions, we have two factors here, m plus 5, m plus 7. And the third factor we start off with is the greatest common factor. All right, so this should kind of remind you of some other topics that we took a look at in terms of zeros. So if you have to find zeros here, because this is more an advanced topic, so you have to find the zeros for this type of expression. Zeros basically means when will this be equal to 0? So when you're multiplying three things together, any one of these items, this one, or this one, if it's the number 0, then multiplying will produce an overall value of 0. That's what the 0 is all about. So to find zeros, we set each individual factor equal to 0. It's a much more sophisticated and complex technique. So we have 2p would be equal to 0, m plus 5 is equal to 0, and then plus 7 is equal to 0, which would produce p is equal to 0, m is equal to -5, and m is equal to -7 for your zeros. Now this is a very complex way of thinking of zeros, very, very different than what we've looked at in the past, but it's just something to highlight for future consideration. All right, just moving along with a couple more things. So the question here is asking to factor each quadratic relation and determine the x-intercepts, or the zeros. Now you can see why we use that technique. So first step is to go through all the factoring, which we will. So in part A, so again, your first question, always look for a greatest common factor. So definitely a -1 for sure, because as we saw in the previous example, that's always a good idea to remove the -1. What about the 3? Is 3 common to this value here? Yes, it is. 3 will divide into 3 evenly, so 3 times 1. What about the 18? 3 goes into 18, 16, 6 times, sorry. So 18 can be written as 6 times 3. So your greatest common factor is actually the negative and the 3. So -3 times the x squared produces the -3x squared. Dividing -3 by -3 produces a +1. Notice that, leaving the x behind, and then +18 divided by -3, -6. So just quickly hide something here for you folks. Don't give away too much just yet. Okay, so now we have a trinomial. Can that be factored? Well, let's see. Two numbers that multiply to -6 and add to +1. Does that exist? Well, two numbers that multiply to -6. One of the numbers has to be positive, one of the numbers has to be negative. That's a guarantee. Two numbers multiply to 6, well, it could be 6 and 1, could be 2 and 3. So you can go through a little experimentation. Here I'm just taking some shortcuts. So the correct numbers are positive 3 and negative 2. They will multiply to a negative 6, and they will add to a positive 1. So this is doing some mental work to try and get this result. So there's the product, there's your sum, and that takes care of the first step, which was factoring the relation. So we went from standard form to factored form. The second part is determine the zeros. And again, that's a matter of setting this entire expression equal to zeros. Remember, zeros are kind of like x-intercepts. So that means the y value would be a 0. So that would imply, well, doing this sort of idea, setting that equal to 0, which then essentially would mean that any one of these three things could be a 0. Now, there's no way of turning a number, negative 3, into 0. That can't happen. But is there a number that when you add 3 will give you the answer of 0? And the answer is yes. Is there a number that when you subtract 2, you can get a 0? And the answer is yes. So it's as simple as solving those equations. And those are your two zeros, or your two x-intercepts. And we've now successfully determined the x-intercepts. So this is where your parabola would cross the x-axis. How do I know it's a parabola? Well, because it's the equation of a quadratic in standard form. Next one, we also have a quadratic in standard form. And again, part of the same question, we're asked to factor. So we have to always look for a common factor first. So it looks like 5 will work. 5 does divide it into 30 and 35 evenly. So again, you can think of this as the division process. 5 into 5 is 1. 5 into 30 produces a 6. And 5 into negative 35 produces the negative 7. Leave those variable portions behind. Again, you have a trinomial here that you have to try and see if it can factor. So you're looking for product value of negative 7, sum value positive 6. So a product of negative 7, there's one possibility. Obviously, you can have negative 7 and positive 1, but you want those two numbers here and here to add to positive 6. So the two numbers that multiply to negative 7 and add to positive 6 are positive 7 and negative 1. So there's process number 1 for factoring the quadratic relation. And then to find these zeros, we want to then set the equation equal to 0 and then solve from there. So again, we have this technique of setting this equal to 0. And we have three different things. We have three different factors. So this could be a 0. No, it's already a 5. Can this be a 0? Yes. If we know what number for x, add 7, you'll get a 0. What number take away 1 gives us a 0? Well, that also exists. And the answers are by simply solving these equations. So x will equal negative 7 will produce a 0 in the first bracket. X equals 1 produces a 0 in the third bracket. So that produces our zeros for our x-intercepts. All right, and moving right along for this last one here. For the quadratic relation given here, we have to determine the coordinates of the vertex, then sketch the graph, including the y-intercepts. So a little bit more going on. So we're not using technology here. So one of the ideas is to determine the vertex. Now, if we had the zeros or the x-intercepts, we could find the vertex using techniques we did back in chapter 3, and then sketching wouldn't be a problem. And the y-intercept, as you remember, is your c-value. So there's the y-intercept. So we already have the y-intercept. You should also know that the parabola opens, correct, up. There's an a value of 1, so the parabola should open up, y-intercept of negative 8. So we have to go through the factoring process to be able to determine the vertex. So the factoring process, we have a trinomial. Two numbers that multiply to -8, add to +2, happen to be +4 and -2. And again, that's a little time consuming, but there's your results there. So there's your factored form, no common factor there. Finding the zeros. So again, setting this equal to 0. So x plus 4 could be 0, or x minus 2 could be 0. We've looked at this before, so you get your x, those are your x-intercepts. Now remember, your technique for finding the vertex would be to average these x-intercepts or zeros, simply because you can then find the axis of symmetry. That was a technique from Unit 3. So this will give us the axis of symmetry, but that's not the complete vertex. So averaging those two gives us the x-coordinate of the axis of symmetry, or sorry, the x value for the vertex, which is our axis of symmetry. And to find the vertex, we need to find the y value. How do we do that? Well, we have a relation given to us. We can simply plug in the x value. Now notice here I chose not to use the expanded form, although I could have to find the y value. I used instead the factored form. It really doesn't matter which form you use, as long as you're confident you got the factored form correct, I suppose. And then once you plug in that x value, you're going to get the y value. So the y value for the vertex is -9. So we have all the information we need to produce a graph. So the graph here will have a vertex at -1 and -9, cross through the x-axes at -4 and +2, axes of symmetry at -1, and it should be opening up since we know the a value is 1. And as a result, there is your graph. Well, a sketch of it anyways. And so there's your axis of symmetry. Parabola opens up, goes on forever. Probably wouldn't be a bad idea to label the axes as well. Little x here, and a little y there. And you've got all your points labeled as best you can. So get all the values in there. And make sure you label all the points as well. Okay, just a little note about the answer. The book is incorrect, so just keep an eye out for little things like that and always check your solutions.